Section 7.4 Functions. Relation, domain, and range. Definition. A relation is a set of ordered pairs. A relation is talking about the coordinates. We have a x and y, that's ordered pairs. The domain of a relation is the set of explanatory variables, and the range of the relation is the set of all values of the response variable. So when we're talking about the domain means we want to find out all the possible values of x. And for the range, that will be all the possible values of the y in here. And remember, for the x, we call this as an explanatory variable. And for the y, that will be the response variable. So you could think about it. X is just like the input, y will be the output. When we have a value of x, plug into the equation, you could find out what is the values of the y. So in general, each member of the domain is an input and each member of the range is an output. So consider the explanatory variable, that will be your input, response variable will be your output. A relation described by a table. So the ordered pairs, we could use the table to represent it. We have a 3 and 2, 4 and 1, 5 and 3, and 5 and 4. So the relation described by the table. Or a relation described by graph. So we have the coordinate here. We could plot the points in the rectangular coordinate system. So the 3, 2, the ordered pairs, we have a 3 unit to the right, go up 2 units. A relation has an input-output machine. So you could think about it. The x here, this is gonna be my input. When I have a coordinate of x equal to 3, we plug into a relation machine. The output, that will be y equal to 2 here. Another coordinate, 4 and 1. So 4, that will be the input. Plug into the relation, the output is gonna be your 1 in here. And these values, the 3, 4, 5, we call this is gonna be the domain. One more time, the domain is the possible values of x. So when we have these 3 guys here, 3, 4, 5, that will be the domain. And then the range, talking about the possible values of y. So y, we have a 2, 1, 3, and 4 here. Note that the input x equal to 5 is sent to 2 outputs. So we have 2 outputs in here. We have a 3 and 4. Okay, so we have a 1 input, but we do have 2 outputs from here. Function. A function is a relation in which each input leads to exactly one output. Highlight this one. Each input leads to exactly one output. We call this as the function. So think about it. For this guy, I have a 1 input, but I got like 2 outputs in here. So you know this is not a function. Example. Designing whether an equation describes a function. Is the relation y equal to x plus 2 a function? Find the domain and the range of the relation. So first, consider some input-output pairs. For example, if I have the values of x, 0, 1, 2, when I plug in 0 to this equation, I got 0 plus 2, so y equal to 2. When x equal to 1, plug into the equation here, y will be 1 plus 2, which is going to be equal to 3. Last one. X equal to 2, plug it in, you're going to get y equal to 4. So you can see each input leads to just one output. And the inputs increase by 2, so the relation y equal to x plus 2 is a function. Okay, one more time. If you know if the equation is a function, you have to make sure they only have a 1 input leads to 1 output. Okay, we are not done yet. After we know this relation is a function, we need to find the domain and the range of the relation. So think about it. What x can be in here for this equation? Is it any number? Once you plug it in, you're gonna get undefined? No, right? X can be anything. You could put like from 0, 1 to 100, 1000, any number. Even the negative number, you could put 0, -1, -2, -100, -1000. It doesn't really matter. So for the domain, this is gonna be the set of all real numbers. All real numbers means like you could put anything on here. And for the y, we're gonna consider the range. The range of the relation is also the set of the real numbers. Since you could put in anything from the x, then when you add 2 here, we still get the real number. So the y, the range of the relation, is also the set of the real numbers. Okay, how about this one? Is the relation y squared equal to x a function? One more time, what is the definition for the function? We need to have a one input leads to exactly one output. So now consider when x equal to 4, when I substitute 4 for the x, and then I'm gonna solve for the y. So I'm gonna take the square root for both sides. I'm gonna get y equal to -2 or y equal to 2. So I have a one input, x equal to 4, but right now I do have a two output, y equal to -2 and y equal to 2. So you know that y squared equal to x is not a function. Okay, it's not a function. To be a function, we only have to be a function, we only have a one input leads to exactly one output. Okay, is the relation described by the graph at the right is a function? So think about it. For the function, if I only have a 1x, I should get only equal to have a 1y here. But when x equal to 2, what happened when x equal to 2? If x equal to 2, I'm gonna go up to hit the graph, y equal to +3. Or when x equal to 2, when I go down, I hit the equation, y is gonna be equal to -3. So that means I only have a one input, x equal to 3, but then I'm gonna get two outputs, y equal to -4 and y equal to 4. So I know the relation is not a function. Okay, vertical test. A relation is a function if and only if each vertical line intersects the graph of the relation at no more than one point. We call this requirement the vertical line test. If I want to figure out if the graph is going to be a function, I could use the vertical line test. This is talking about when you draw the line on that graph, if I only hit one point, only hitting one point, so that will be the function. If I hit the graph more than one point, that means this is not a function. If I draw the vertical line here, you're gonna see I'm gonna hit the graph 2 points. So you know this is not a function, and we call this as a vertical line test. Okay, let's try the example. Determine whether the graph represents a function. So I have the circle in here. Now I try to use the vertical test. I'm gonna draw the line in here. Okay, how many points are gonna intersect the graph? I have 1, 2. More than 1 points, right? So we know that the relation is not a function. This is not a function because I hit like 2 points in here. You could think about it. When x equal to 3, I get 2 points in here. Y may be equal to about 0.8. Another point will be 4.2. So 1x equal to 2 outputs, I have a 2 y's. So I know this is not a function. Okay, how about the question 2? Try to graph a vertical line here to see if they're gonna intersect more than once. Okay, I draw the line here. I only have a one intersection point. Here, only one intersection point. Here also, I only have a one intersection point. So by the vertical line test, my vertical line only intersect the curve at one point. So I know the relation is a function, okay? So this is gonna be my function. Okay, linear function. A linear function is a relation whose equation can be put into the form y equal to mx plus b, where m and b are constant. We learned this one from the previous session, right? This is gonna be my linear equation. M represent your slope, b represent your y-intercept. And I know a linear function is a relation whose equation can be put in this form. That means when you know if this is a linear equation, the relation is a function. Okay, the relation is a function. Observation about the linear function y equal to mx plus b. First, the graph of the function is a non-vertical line. Number two, the constant m is the rate of change of y with respect to x. Of y with respect to x, means the change of y over the change of x in here. Number three, the constant m is the slope of the line. The absolute value of the slope is a measure of the line's steepness. Number four, if m greater than 0, the graph of the function is increasing. Remember we talked about it on the session 7.3. When the line is going up, is increasing, the slope is become positive. If your slope less than 0, the graph of the function is a decreasing line. So when we have a decreasing line, it's going down, you know the slope is going to be negative. And if your slope equal to 0, the graph of the function is a horizontal line. So when we have a horizontal line, the slope is going to be equal to 0. And y-intercept of the line, we know that's our 0, comma b. Okay, y equal to mx plus b. The b will be your y-intercept. Okay, rule of law for functions. We can describe sum of all of the input-output pairs of a function by means of, we could use the equation to describe it. For example, y equal to mx plus b. This is going to be equation, and this is described like the input-output pairs also. A graph. We could draw a linear equation on a graph, so we could look at it, the input-output pairs also. A table. For the table, you could use a ordered pairs to represent it. For the works, for example, I have a y equal to 3x plus 2. So we're gonna say y equal to 3 times the variable of x and then adding 2 here. And these four ways to describe input-output pairs of a function are known as the rule of 4 for functions. Okay, let's try the example. Is the relation y equal to negative 2x minus 1 a function? Y equal to negative 2x minus 1. So this is equal to y equal to mx plus b. So you know this is a linear equation. And I know all the linear equation is a function. Number 2, list some input-output pairs of y equal to negative 2x minus 1 using a table. Okay, So for the table, I'm gonna plug in these 5 points here. You could make up any values. Okay, you could do 0, 1, 2, 3, 4. And then plug it into the y here. Find out what is the output of your y. So you could get this. So this is list the input-output pairs using the table. And then using a graph. So I have the coordinate for the number 2 here, right? -2, 3, -1, 1, 0, -1. So I'm gonna put these 5 points onto my graph. And then I'm gonna connect all these 5 points together with the straight line. So this is describe the input-output pairs using a graph. Okay, last one, by words. So for each input-output pair, the output is 1 less than -2 times the input. Example, finding domain and range. Use the graph of the function to determine the function's domain and range. First, we need to find out the domain. Domain means all the possible values of the x. So look at the x-axis. For the graph here, what values is going to be the smallest values for your x? The smallest values here, that will be -4. And since there's a no breaks in the graph here, so the smallest values of the 4 from here, we're going to keep going until this point. So this is going to be the larger values of your x, so that which is going to be equal to 5. So I know my domain, the x is going to be in between -4 to 5. -4 to 5. This is talking about the domain. And how about the range? Range is talking about the possible values of the y here. So look at the graph, which one is going to be the lowest point? The lowest points, that will be 5 and -3. How about the highest point? Highest point will be 2 and 4 here. So we only pay attention for the values of y. So I know my range is going to be y in between -3 to 4. Okay, -3 to 4. This is going to be your range. Okay, number 2, finding the domain and the range. To find the domain, we're going to pay attention for the values of the x. And for the graph here, you're going to see these 2 arrows. That means the graph extends to the left and right indefinitely without breaks. So for my domain, that will be all real number. Okay, all real numbers means any number can be possible values for your x in here. Okay, look at the range. Range, we're gonna pay attention for the y-axis in here. What is the lowest point? The lowest point is gonna be 1 and -3. So you know the y, the smallest value of the y will be -3. Since the graph is going to be extend indefinitely, so we don't have the highest point of the y in here. So we're going to say the range for the y is going to be greater than or equal to -3. Function notation. Rather than using equation, table, graph, or words to refer a function, we learn the function. We use the function of x. Okay, or we call this as f of x to represent your y. We're gonna write it to y equal to function of x. For example, if we have the equation y equal to 2x plus 1, okay, this means y equal to mx plus b. You know this is a linear equation. We're gonna replace the y with the f of x in here. So we're gonna write it one more time. This is f of x equal to 2x plus 1. And we call this is the function notation. And the notation f of x does not mean f times the x in here. It is another variable name for the y. Okay, y is equal to f of x. We just replace for the y with f of x in here. And think of the function as a machine that send inputs to the outputs. You could plug in anything from here. This is going to be your input. And then plug into the linear equation. You're going to get the output from here. And for any function, for example, if I want to find f of 4, it means we want to find the function when x equal to 4. Okay, one more time. When we want to find f of 4, that means x equal to 4. You want to plug in x equal to 4 for your linear equation. Find out what is your y equal to. Let's try the example. Okay, so we have the function notation here. We want to find it out at 5, means I want to find f of 5 in here. I'm gonna plug in x equal to 5. So plug in x equal to 5. Okay, do the math here. Negative 4 times 5, you're gonna get negative 20. Negative 20 plus 2, you should get negative 18. So f of 5 will be equal to negative 18. Okay, try these functions. I have f of x, g of x, and h of x. So I do have a few functions in here. And I want you guys to find the followings. Try to do it by yourself first, and then we're going to check the answer. Okay, f of negative 2, you want to plug in x equal to 2 for the function of f. So plug in here. X equal to negative 2. Make sure when you plug in x equal to negative 2, put the parenthesis. This is a negative 2 squared. Okay, so negative 2 times negative 2 and times positive 2 here. So do the math. That will be 4, positive 4. And then 4 times 2, you're going to get the x. Negative 3 times negative 2, you're going to get positive 6. Add it up. That will be 14. Do the same thing. This time, that will be the function of g. Okay, plug in x equal to 3 for the g of x. Plug in x equal to 3. Do the math here. 4 times 3, you got 12. 12 minus 2, you're going to get the 10. 5 times 3, minus 1. So 15 minus 1, you're going to get 14. Simplify it. That will be 5 over 7. Number 3, h of a. So this time we are not plugging to the constant. We're going to plug in another variable, but it doesn't matter. We could just replace the x with the a in here. So h of a will be equal to 3a minus 5. Number 4, h of a minus 2. This time I want to plug in the whole thing, a minus 2 into the function of h. So you're gonna replace the x with a minus 2. Okay, we paste the x with a minus 2. We're going to replace the x with the a minus 2. Then, we're going to combine the 9 terms. So first, we want to distribute for the 3. So we have 3a minus 6 minus 5. Combine the 9 terms. You're going to get 3a minus 11. Okay, next example. Some input-output pairs of the function g are shown in the table. So this is x, represent your x. G of x means your y in here. So first, find out g of 7. G of 7 means when x equal to 7, what is your y equal to? So look at the table. X equal to 7, Y equal to 12. So G of 7 equal to 12. Number 2, find the x when g of x equal to 9. This time they given the y here. Y equal to 9. What is your g of x equal to? What is your x equal to? I do have a two outputs that's equal to 9. One is x equal to 4. One is x equal to 6. So we have both inputs lead to the outputs y equal to 9. Example, using a graph to find the value of x or f of x. A graph of a function f is sketched below. Number 1, find f of 4. So if they want to find f of 4, means when x equal to 4, what is your y equal to? So x equal to 4, we're going to start from here. X equal to 4, we're going to go up here the linear equation, go to the left. You're going to see y equal to 3 here. Means f of 4 will be equal to 3. Next one, f of 0. So this means we want to find the y when x equal to 0. So x equal to 0 is going to be here. And then we go up, we hit the line here, and y equal to 1. So f of 0 equal to 1. Okay, number 3. Find the x when f of x equal to negative 2. This time they given the y, and I want you guys find out the x. So y equal to negative 2. So y equal to negative 2 like here. And then we're going to go to the left, hit the linear equation, go up. This is going to be x equal to negative 6. Okay, another one. Find the x when f of x equal to 0. So this time, y equal to 0. What is your x equal to? Y equal to 0, talking about like here. Go to the left. X will be equal to negative 2. Definition. The response variable of a function f can be represented by the expression formed by the writing the explanatory variable named within the parenthesis of function here. Response variable will be equal to the function of explanatory variable. So remember we call x, that will be the explanatory variable. Y, that will be the response variable. So you could just think about like this. The number you plug in for the function of something, this is gonna be your values of the x. After you plug it in, you're gonna find the response variable, which is gonna be your y here. And again, we call this is the function notation. Okay, example. Let p equal to negative 0.45t plus 36.83 be the equation that models the percentage p of American adults who smoke at t years since 1970. The table below shows the data. Verify the graph of the p comes close to the data points. First, we want to sketch the scatter plot using the table here. So here, t years since 1970 means t equal to 0 since 1970. And then we're gonna use another table to use the year with the t. So t equal to 0 when 1970 here. So how about 1980? What is your t equal to? You could do the subtracted 1980 minus 1970 equal to 10. So that's why I'm gonna get the 10 in here. Figure out what is t equal to when 1990, 2000, 2010, and 2012. You should got this. Okay. Now we're gonna use this coordinate to construct a scatter plot. Make sure your scatter plot have the title, label the x-axis, and label the y-axis. You should have the picture like this. Okay, 0, 37.4, 10, 33.2. So 10, 33.2. So we have the scatter plot. We want to graph the linear equation. Okay, so now I'm going to use my table here. I plug in t equal to 0. Plug in t equal to 0 into your linear equation. The first p equal to 36.83. So I'm gonna make up two more points, t equal to 30 and t equal to 40. So plug in this linear equation, figure out what is your p equal to. So you should get 23.33. Another one, you should get 18.83. So now I have these three coordinates. And then I will be using these three coordinates, draw the straight line from here. You should have the pictures like this. Okay, after we have the scatter plot with the linear equation, we want to verify if the linear equation come close to the data points. You could see all the points is going to be around the straight line. So we say the line comes close to the data points, so the model is a reasonable one. Number 2, we write the equation with the function named g. So I have the linear equation in here, and we want to use the function of g, but keep in mind we don't want to use the g of x, because right now we are using the t as our explanatory variable, and then the p will be the response variable. So when you're using the function of g, you're gonna put g of t. Okay, the t is talking about in this guy here. So that will be g of t equal to negative 0.45t plus 36.83 here. Number 3, estimate the percentage of American adults who smoked in 2011. So 2011, we want to use like this linear equation, but remember the t here. But remember the t equal to 0 since 1970. So right now we want to find out the 2011. What is your t equal to? So we're going to use 2011 minus 1970, which is going to be equal to 41. So now we're going to plug in 41 into this linear equation. What is a g of 41 equal to? Use your calculator. You should get 18.38. So that means the model estimates that 18.38% of American adults smoked in 2011. Okay, number 4. Find the p-intercept of the model. What does it mean in this situation? So we have the linear equation here, and we could see this is gonna be your p-intercept. Okay, y equal to mx plus b. So this guy will be your p-intercept, and the intercept is going to be 0, 36.38. And what does it mean in this situation? So we're going to say the model estimates 36.38% of American adults smoked in 1970. This estimate is fairly close to the actual percentage, 37.4%. So we could double check for the 1970, we got like 36.38%. Here, 1970, we got 37.4, which is really close to our estimate. Okay, example, a store is open from 9 a.m. to 5 p.m. Monday through Saturday. Let L equal to function of T be an employee's weekly income from working T hours each week at $10 per hour. Find the equation of the model f. So I want you guys figure out what is the linear equation. And then they're working T hours each week at $10 per hour. So means if you're working 1 hour, you're gonna get $10. 2 hours, you're gonna get $20. 3 hours, you're gonna get $30. So right now you're working on T hours. So that will be f of t equal to 10 times the t. Find the domain and the range of the model f. So first, we figure out what's the domain. Think about it. The store open from 9 a.m. to 5 p.m. There are 8 hours a day. And then they work from Monday to Saturday. So 6 days a week. So when you multiply it 6 days a week and 8 hours per day. So when you multiply it, they should have a 48 hours. So for my domain here, that will be the set of the number between 0 and 48. The t will be in between from 0 to 48 hours. Okay, how about the range? The range, that will be your output. If they're working from 48 hours, you plug into this formula. The range is in between from 0 to 480. The graph at the right isolates the domain and the range of the model f. So you could look at this picture. For the blue line here, this is the linear equation, function of t equal to 10t. And then we just pick some hours in here. When t equal to 22, you plug in here, you're gonna get 220. When t equal to 35, you plug in here, you're gonna get 350. And then since they work 8 hours a day, 6 days a week, so we do have a 48 hours for total. Okay, so they're gonna start from here. And then the domain means you want to find the possible value of t here. So you could see the straight line here. The lowest point is gonna be 0. The highest point in here, that'll be 48. So the domain is gonna be in between 0 to 48 hours. And for the range here, look at the possible values of the I in here. The lowest point is going to be 0, 0, which is going to be the 0. The highest point, that will be 480. So my range is going to be in between 0 to 480. That's it for the session 7.4.